Let's take a look at Coulomb's law and effective nuclear charge. We care about this because, of course, periodicity is a big topic on the AP exam, and we want to be able to understand these reoccurring trends and justify the underlying cause, and often we will use Coulomb's law in our justification. Coulomb's law, of course, states that the force of attraction between two oppositely charged particles is, and these particles that, of course, we're referring to will be the nucleus and the electrons. And so this force is proportional to, let's get the yellow highlighter going, directly proportional to the magnitude of the charges. That in particular refers to the size of the proton charge, because our electron charge will generally be referring to only one electron at a time, and that will be constant, but the proton charge will of course change from atom to atom. Further, we need to pay attention that we're inversely proportional to the distance between these two charges. Again, the distance that we're referring to will be the distance between the nucleus and the electron. Coulomb's law can be used for much broader applications, but we're sticking with periodicity here. Let's be clear that we will never need to put numbers into this formula. We simply want to use it in support of statements that we make as we're discussing periodicity. So what is effective nuclear charge? Generally symbolized by Zeph. I will use ENC throughout my videos because it's easier to type. It's an approximate determination of the nuclear charge that's actually transmitted out to any electrons for that matter, but generally refer to the valence electrons, transmitted or leaked out to the valence electrons. How do we get this? Or why does this even happen, of course, would be a good question first, because some of the nuclear charge is blocked or shielded, we'll hear about shielded, by the inner core electrons, the electrons between the nucleus and the valence electrons. How do we calculate this? Number of protons minus inner core electrons will equal effective nuclear charge. And you can do that math, but for all intents and purposes, as far as we're concerned, in any atom, this value is approximately equal to the number of valence electrons. Of course, for the valence electrons, the effective nuclear charge will be equal to the number of valence electrons. Let's have a look and see how this comes about. So we'll look at lithium first. Lithium in the first in the first column of the periodic table has 3 protons and an inner core, 3 protons total, an inner core of 2 electrons, that's those right here. And so ultimately the valence electrons feel an effective nuclear charge of 1. If we proceed down the periodic table to sodium with its 11 protons, and this time an inner core of 10, this being our inner core. And so the valence electron, what actually gets out? The nuclear charge, some is blocked by the inner core, and what actually leaks out to the valence electrons is 1 plus. Same happens with potassium, also in the first column of the periodic table, with 19 total protons, an inner core of 18. What does this valence electron experience? Again, 1 plus. 19 minus 18, 1 plus. Let's look again, this time at group 2. And so we'll take a look at beryllium. I see an error. 4 plus, 4 protons with an inner core of only 2, essentially shields or screens, and the outer valence electron experiences an effective nuclear charge of 2. Magnesium will also end up with 2 because of the 12 protons total, with an inner core of 10, what actually makes it out to the valence electrons would be approximately 2 plus. Let's take a look at the last one. And this time we'll take a look at the third column in the periodic table, boron, aluminum, gallium. As one more example, I see an error one more time. That should be a 5. And so 5 plus with an inner core shield of 2, what in a sense or effectively makes it out would be 3 plus. An effective nuclear charge. The valence electrons experience an effective nuclear charge of 3. Same for aluminum, and so on. Here's our summary, is that the effective nuclear charge increases across the periodic table and is approximately equal to the number of valence electrons. Here's the values. And so we definitely want to have the concept that ENC increases across the periodic table, of course, because of an ever increasing number of protons.